So let's continue our discussion of different versions of OCT. So previously we discussed time domain OCT, where you move a reference mirror and get data as a function of the mirror position. That is the first type of OCT that was invented. The sure one of the problems with that OCT is that it's you keep having to move some mirror, right? So mechanically, if you have to move something, it takes time, and so it's slow. It can be slow, even if you use a high-speed movement. Like, so is it the question was that the engineers asked was, is it possible to build a new kind of OCT system which does not have a moving mirror at all? So that way it can avoid, like it can be much faster than so the short answer is yes. People figured out how to do this. It took a long time, but people had to invent some other new technologies to get this to work. But basically, this is what's called a spectral domain or Fourier domain OCT, which allows you to, like, so instead of having a mirror, which is this is the reference mirror, instead of moving the reference mirror, you actually keep it fixed. Then how do you get depth data, right? Like if you just keep it at one person, then how can you possibly get data? So the answer is, instead of one detector here, you can use say 100 or 1,000 detectors called a spectrometer. So what you do is like what the like taking one, like moving the mirror 1,000 times and getting 1,000 data points. Instead of that, in one measurement, you split the light into 1,000 different wavelengths or wave numbers and get data at every. So in parallel, you get 1,000 measurements on the spectrometer. So instead of with one single detector, you use 1,000 detectors, and that kind of the. I'll tell you how it works, but the basic idea is that instead of moving the mirror to different positions, you use a spectrometer to get more data, and from that you can figure out depth positions. Okay, that's the crux. That's the essence of what people figured out. And the way it works is, let's say this distance is d. Look at a position which is the same distance d over here. Let's draw a dotted line at this position. Okay. Now, if the sample is slightly off from that position by a distance delta L. Okay. So now, what happens to the light that comes back? Okay. So let's look at what happens. Let's say just if you have a single detector, one detector at a time, let's see what happens. Okay. So now, imagine if you have a wave that is going in. If the mirror position is, or if the sample position, layer position is something of this sort, then there is some phase of light here. It goes here like this. It hits this. It scatters back. It comes back. So if if this length delta L is lambda or 2 lambda or 3 lambda for that one wavelength, then the light that is coming in this way and light that comes back this way, they will interfere constructively, right? If it's like this, or if it is also like this. So if it is multiples of lambda, 2 lambda, 3 lambda, it will go here, hit the scattering, like this layer, and come back, or like depending on delta L. If delta L is equal to lambda 1 or 2 lambda 1 or 3 lambda 1, it will be constructive interference. For a different wavelength lambda 2, if it's lambda 2 or 2 lambda 2 or so on, it will be constructive interference. Okay. So for some wavelengths it will be constructive interference, some other wavelengths it will be destructive interference. For example, to give you a third one, if the wave is such that it goes like this and it hits and it comes back like this, and this may be destructively interfering. So light it goes forward, light that comes back, or goes to the mirror and comes back. So basically, if the phase difference is like 0 or in like 2 pi or something, then it will constructively interfere. If the phase difference will kind of is minus pi, then they will kind of or pi, they will destructively interfere. So for some wavelengths, there will be constructive interference, some wavelengths will be destructive interference, some it will be in between. So what you do is, as a function of wavelength or 1 over wavelength, if you make a plot of the, like what you will, which wavelength will be constructive, which wavelength will be destructive. So some wavelengths it will be constructive, some it will be destructive, some will be constructive, destructive, and so on. It will be like a sinusoidal pattern as a function of frequency, 1 over wavelength. Okay. So as for different wavelengths, there will be constructive or destructive, constructive, destructive. So that's constructive, destructive, constructive, destructive, somewhere in between. Like so, it's a sinusoid in the frequency domain. So this is the frequency axis. X-axis is not Z position; it's the frequency, not the mirror position. It is frequency. In the frequency domain, you have a sinusoidal pattern. Okay. Now the thing is, this delta L is a distance, and this is a frequency, right? So it turns out that there is a Fourier transform relationship between the frequencies. So if you take a Fourier transform of this, you will get some data, and the frequency of this is actually proportional to delta L. So the larger this frequency, the larger the delta L. The smaller the frequency, the smaller the delta L. So basically what you have is constructive and destructive interference at different wavelengths, and consequently the frequency of this, how often it changes, it is decided by this delta L distance between this position, like the reference 0 position and the sample layer position. Okay, that's the essential. So so in frequency domain, if there is a sinusoid, if you take the Fourier transform, it will be a peak. It's a delta function, right? If you take what's the Fourier transform for shifted delta function, it's a sinusoid. Complex exponential, the sinusoid. So basically, that's the reason why it's called Fourier domain OCT. So you collect data in the frequency domain as a function of wavelength or wave number. Like let's say wavelength, and then 1 divided by wavelength is wave number. So collect data as a function of frequency, and then take the Fourier transform, and then you will get the location of your layer, like where the location of the reflection, the reflective layer. So if a layer is at this position, you get peak at this position. If you have multiple layers, you will get multiple peaks, each corresponding to one layer. Okay, so this is the essential idea behind what's called Fourier domain OCT. Okay, and the difference in terms of instrument is, instead of one detector where you move the mirror, you have a device which will spread out the light into different wavelengths. Each wavelength has one detector. So as a function of detector, imagine you have a bunch of detectors which are in an array. Like the light comes in, it is spread out into different, so lambda 1, lambda 2, lambda 3, and so on, lambda n. So each of these is spread out, and so like you have a bunch of detectors, and each of these detectors, you can, from this detector data, you can make a plot of this sort, then take a Fourier transform of that data, you get the position of layers, which, like, where is the layer 1, what is the location of layer 2, layer 3, and so on. Okay, so this is the essential idea behind Fourier domain OCT. Any questions? I'll go into more details, but is the basic idea clear? Okay. So here is kind of like how this instrument is constructed. So you have a broadband source of light. The source of light, at least in this version, is exactly the same as before. You have not just one wavelength, but multiple wavelengths incident. It goes through a beam splitter. It goes through a mirror. This time the mirror is fixed. It's not moving. Then it goes, and it also goes to the sample. There are multiple layers inside the sample. Each layer reflects or scatters back some light. You put it, instead of putting a detector here, in terms of the instrument construction, the only thing you have done is keep the mirror fixed. Instead of one detector here, you put a array of detectors. So how can you make split the light into different wavelengths? You can use a prism, for example, right? Prism splits light into white light into yellow, that's rainbow colors. So you can, it's also true for infrared. You have infrared light come in, you can put a prism which is spread it out into all the different wavelengths of infrared. It's the same basic idea. So that way you can you can use a grating, you can use different ways of spreading out the light. But each wavelength will go into a different detector, and this way you can fully kind of get a sense for what the data looks like. Okay, so each wavelength is separated out into different buckets, and then you get data as a function of frequency. And then you take the Fourier transform or the inverse Fourier transform in this case, and you get this layer 1 and layer 2. Here you will get peak 1 and peak 2. So each layer will give you a peak in the after the inverse Fourier transform calculation. Okay, so this is the basic idea. Okay. So there is this is one version of new version of OCT. It is much faster than the previous version in terms of getting overall data for the same quality of data. You can get much faster. There is another version which you can do the same kind of thing, but you can use a different type of laser. This is what's called swept source OCT. This is a version of OCT. So they were trying to solve this problem of not needing the moving mirror. If you keep the mirror fixed, then how to get the data? So this also does the same thing, but in a different method. Okay, so the way this works is in the first method, you have all wavelengths incident at the same time, and then split the wavelengths at the end into using a prism. You separate out all the wavelengths. Instead of doing that, you use a new kind of laser. They had to invent a new laser which emits one wavelength at a time. Wavelength 1, wavelength 2, wavelength 3. It will immediately one after the other, it will emit it very fast. Okay, wavelength 1 and then wavelength 2, wavelength 3, wavelength 4. It will emit one wavelength and next. So it's what's called a swept laser. It's a new kind of laser which was invented for the purpose of doing this type of OCT. And so this frequency swept laser, so it emits wavelength 1, emits wavelength 2, emits wavelength 3, emits wavelength 4, and so on. So one after the other. And as soon as this emits the wavelength, it goes through the sample, go through the reference. There is only one detector here. So instead of spreading out the wavelength, you take, instead of in space separating wavelengths, in time you separate wavelengths. So time 1 and point T, you get detector like measurement as corresponds to wavelength 1. Time point T2, get wavelength T2, which is lambda 2. Okay, so you just separate it out in time, and that way it's you change the wavelength, make a measurement, change the wavelength, make a measurement, change the wavelength, make a measurement. So this is done electronically, so it's done very, very fast. It's done like kilohertz or even megahertz speed. So you do it like sort of basically a million times every second, or 100,000 times every second. So it can happen. Although I'm saying it slowly, it happens it's almost like boom, like very fast. It sweeps across all the different wavelengths, and every point it collects data. So one wavelength, one data point, next wavelength, next data point, next wavelength, next data point. Okay. So it as a function of time, you get detector signals and do the same thing. So make a plot of as a function of time, make a plot of different. So basically, time is also equivalent to wavelength in this case. Okay, so 1 over wavelength. But as you change the wavelength, you can get a plot. The same principle is there. So this reference mirror is fixed. There is a sample layer here. depending on this distance delta L, there is constructive, destructive, constructive, destructive interference. So if this delta L is very big, if this is big, then you'll have very high frequency. Let me erase that, okay. Sorry, yeah. So if, say, delta L is very small, if this is the reference position, if the delta L is small, then you'll have low frequency as a function of time. If delta L is very big, like so at this distance over here, then this is large, so you'll have very high kind of high frequency. So by taking a Fourier transform of this low and high frequencies, you can get how deep the layer, like layer 1 is, layer 2 is, layer 3 is, and so on. So this is how you see. So that's essentially what is plotted here. So at any given time, there's one wavelength coming in. It's a swept source. It goes to the reference mirror, comes back, get a detector, get 1 point. At one time, you get 1 point over here. Then another, like change the wavelength, get another point. Change the wavelength, get another point. Change the wavelength, change. So you basically, as a function of time, you get different points. Then take the inverse Fourier transform and you get the sample layer positions, these positions. Okay, so this is the second way of, both use the idea that you split wavelengths. In one case you use laser to but the same resistor. In the other case you use the same old laser but use a prism to split the light into different wavelengths. So whatever method you use, so those are two different methods, common methods that people have figured out. And these, because they have fixed mirror position, and also there are other advantages that I'll talk about. So this way of collecting data happens to be much more efficient than time domain OCT. And I'll show you mathematically, like, or at least results, papers which show that these two versions, they perform very well. And these are in fact today's the standard ways of OCT in for clinical or any kind of application uses these either spectral domain or step source OCT to collect all data, all hospitals wherever you go. These are the two ones. The time domain version, the first one which was invented in the 1990s, is not as commonly used today because it's slower. So the faster versions are the one which are actually used in most of the all the new instruments which are made today. Okay. Yeah. So the next thing I want to touch upon. Any questions so far about step source or spectral domain OCT? Okay. So the next thing I want to talk about in the next few slides is the theory of OCT. How this OCT so come up with resolution. How is how do you make what matters, what doesn't matter, those kind of things. So this is for any kind of version of OCT, the same principles will be true. So you have a light source, it's emitting a field which has some profile, and basically light comes in, gets split into the reference arm, goes to the sample, comes back, combines and goes to the detector. This is basically how all of these work. So how much of the light goes through here is given by ER. So if E is the field, ER is the reference arm field that goes to the reflection to the reference reflector, and it comes back like this and it goes through the beam splitter towards the detector. Similarly, the light that comes in here, the field is E, the electric field for example, it goes through here, it gets from every layer, there is a back scattering happening. So you have multiple signals that come back. Only one signal goes forward, but multiple signals that come back, each one from okay, so basically this ES sample, the field from the sample is given by whatever is going forward, whatever is incident on it, times the reflection from first layer plus the reflection from the second layer plus the reflection. So if the S1 is the distance to the first layer, ZS2 is the reflection to the distance to the second layer, and so on. So the reflectivity, if it is Rs for each of these layers, then basically what you get back is a convolution of the reflection or reflectivity at each of these layers times how much space has accumulated, how much distance has traveled. So when that travels a certain distance, there is a certain, how do you know how much it has traveled? There is a certain phase change in light, right? So the distance is equivalent to phase change. So there is, so e to the I 2 pi 2k Vs. So that amount of phase is accumulated. That term tells you how much distance the light has traveled. So basically this equation tells you like it's a combination. This is a combination of all the different layers, how much light comes back from all the different layers. So we have light from the sample. You put them together, ER plus ES goes to the detector. At the detector, you make an intensity measurement. So take the magnitude square. Okay. So that's what is happening here. So that's the theory. So light goes into the reference arm, comes back. Light goes into the sample arm, comes back. They add the interference with each other. Interference is just addition of waves, and then you take the magnitude square because the process of making a measurement is equal to taking the square of the field. That's the definition of a measurement. Okay, so therefore you have it. So there is an average over a certain amount of time. That is for kind of that's a statistical average. We won't go into that for now, but basically that's what the detector does. It takes the square of the field, and therefore if that happens, if you look closely at what happens in each of these, like inside the sample, it looks something like this. You have Rs of Zs, which consists of the reflection coefficient in something. The reflectivity at delta of Zs minus Zsm. Okay, so basically, how much distance is what is the location of the sample layer 1? What is the location of the sample layer 2? Z1, S1, S2, S3, S4, S1. So it's an addition of, so the overall reflection is an addition of reflection from the first surface plus the second surface plus the third surface. So the summation is the addition of all the different reflections that happen. And this first reflection is happening at ZS1, second reflection is happening at ZS2, and so on. So that's what this term means. So you add up the reflections from all the different layers inside. That's the overall reflection of light that happens, and the reflection times the optical path length that it travels. For each of the distance, there is a certain phase change. So this convolution essentially takes that into account and gives you a phase difference corresponding to the distance. And in the end, you get something of this sort. Okay. So this looks a little bit complicated, but let me walk you through this. Okay. So ER, the field from the reference, depends on the reflectivity of the mirror times ZR, like some phase which is proportional to ZR, the reference mirror distance. So this distance here, what is the distance that has lighter? Let me use this color. Okay, what is this distance from the beam splitter to this? That distance is basically given by this ZR over here. So that is the first term. The second term, yes, the light that comes back from the sample arm is a summation of reflection of RS1, the reflection from the first surface times like distance ZS1. So how much phase is accumulated in the first surface, S2, and how much ZS2. So reflection from first surface and how much phase is accumulated. So it will reflect in the second surface, how much phase is accumulated in the second, and so on. It's an addition of all these reflections. That's the overall light that comes back. Okay, that's the equation for ES. So and the detector is ER plus ES. Add the two and take the magnitude square. And so if this is a square, right? So A plus B square is A square plus B square plus 2AB. You can use that kind of AB plus BA. So you can use that kind of a formula, expand it out, and so you're essentially doing some substitutions, and you get this kind of a equation. Let me pause here. Any questions so far? Sorry? Sure. Yeah. Sure. Oh, yes. So in this case, we are assuming that z equal to 0 is the location. So let me point this out. Z equal to 0 here. We are assuming that this is the location, the reference position. You can have it at any, like it's like where is the origin of, where are you starting the x-axis or y-axis, right? Like on the z-axis. So basically, you can choose wherever you want. In this case, we have chosen it to be this position. Okay. Okay. Yes. So this is the beam splitter. So the middle of the beam splitter. So the middle of the beam splitter is z equal to 0. Why? Yeah, so it's of the light that comes in, 50% goes here, 50% goes here. That's what 50-50 beam splitter means. Some amount of light comes in, 50% goes to the reference, 50% goes to the sample. Okay, and whatever comes, 50% goes forward, 50% goes down. So all it does is split 50-50. So for practical reasons in some other system, you may have, like, say, 75-25 or something like that, where 75% may go in one direction, 25 may go in the other direction. That's also, so basically, that's something you can choose. You can have 50-50 splitters, 90-10 splitters, 75-25 splitters, whatever you want. So there are different options you can buy, and so that's available for you to buy. And so you can, based on the experiment, so there are ways in which you can choose how, like there are details of how to build the system where you can choose different splitting, like, how much the light it is. Okay? For practical reasons, in fact, often it can be like 75-21, 90-10. But the principle is the same. So split the light in half. And okay, and the theory is the same for all different versions. Any other questions? Okay. So now what happens is the field from the from the first one and the field from the first reference arm and the sample arm come together, and they get reflected, they get added up and squared, and in the process you get, like, if you actually expand the terms. So bear with me, this looks a bit complicated, but it's actually not very. It's like you can ignore most of it, and there are only some things which matter, and I'll get to exactly what that is. Okay, so basically this as a function of the frequency. So the detector intensity as a function of frequency has so many terms. So reflection from the reference, reflection from the first surface, second surface, third surface, so on. So each of them gives you some contribution. So the first term basically is just the light that comes back. Add up all the light that comes back, that's one value. Then this for the cross, these are the cross terms. Okay, so these are the crucial terms. In fact, the first one is really the most crucial term which matters. And so this one has reflection from the reference times reflection from the sample, one layer of the sample. Okay, so these set of terms, the summation, the set of terms is a cross term. So one from the sample and one from the reference. So you are multiplying one of the field from this times field from this, and then plus the field from the S2, field from the reference. So field from this times field from this. So it's R times RSN, RS1, RS2, and so on. So basically it's they are called cross terms. So one, it takes into account first reflection from the surface, surface inside, and then the reference times the reference. So these terms each, and they correspond to the difference in distance between the reference arm. How much light has traveled? What's this distance minus what's this distance? So that is what determines how much this one first term. So basically this encapsulates. And do you notice what this is? E to the I something. So do you remember what e to the I theta plus e to the minus I theta is? For Euler's identity, right? So you can see that this is a cosine term essentially. Okay, so basically, yeah. So it's a cosine term which has which depends on the distance between the reference arm, the difference in distance between the reference arm and the sample layer. So that's what this captures. This particular term captures each of the how much light is reflected from different layers, and these ones are from S1 and S2. So this is the kind of term where the light that interferes between the first layer and the second layer and the third layer and the fourth layer. The thing is, in practice, RSN is very small. How much of light scatters back from any layer is small. So when you take a small number and square it, it becomes much smaller, right? So therefore these terms can be ignored because it's square of a small number. Okay, so these terms are often ignored. This is just the total light that comes back. So it's like DC, a DC value, a constant value. So this is the only thing. So if you think of it as a graph, so you have a high DC value, a constant value. On top of the DC, there is a cross terms. So there is a small variation on top of a big DC. So this tells you the DC, and this term tells you the oscillation on top of the DC, like the AC term. Okay, and this is the last term is small. Okay, so to summarize, what I'm saying is that although all this looks complicated, you can interpret each of these separately. So this corresponds to the DC, this corresponds to the cross term, and this corresponds to the what's called autocorrelation terms, which is small. Okay, in that sense, and this is just a cosine function which depends on the difference in distance, and therefore this is this becomes a much simpler kind of an expression, which is easy to understand. And so this is essentially this is what gives you the data. Okay, so this is the nature of the data you get from the OCT system. On a related note, so there is a function called gamma, which so if you think of this kind of a curve which I showed you, which you have seen a few times before, what is the width of this kind of curve, right? So this curve is we call it gamma of g, which is also called the coherence function of the source. So this is a property of the source. So the broader the bandwidth, or the larger the number of wavelengths present in the light, the shorter this curve, this width of this curve is, and the fewer the frequencies present. So if you have just one frequency or one wavelength, it will be infinite in length, right? So this will be going on forever. The gamma function will basically be the same. But if you have a lot of frequencies adding up together, then it will be very it may be just very sharp. Okay, so this gamma function, this function over here, is actually kind of related to the spectrum of light. So S of k is basically what are the different wavelengths present in your light. So this is frequency, what are the range of frequencies. So it's the spectrum of the light source that is you are using for your experiment. And so this is the kind of relationship. So it turns out the relation, the coherence length of your light source and the spectrum of light of the light source. So this is not obvious as to why is this shape intuitively you may be able to why shape related to the spectrum, the different wavelengths of light that are incident. So this relationship happens to be a Fourier transform relationship. The fact that there is the Fourier transform of the spectrum power spectral density is equal to the coherence function of the sort is in fact was discovered by discovered and is called Wiener-Kinchen theorem. Okay, there is an interesting history to this. Norbert Wiener was a very famous mathematician in the early 1900s, and like sort of so Wiener and Kinchen, they in 1934 or so, they came up with a theorem called the Wiener-Kinchen theorem, which relates the spectrum of light or a spectrum in general spectrum to the what we in optics call the coherence function. And so this, but it turns out yeah, about 20 years before that, in 1914 or so, Einstein had actually figured all this out, like the relationship between the spectrum and the coherence function. He had already had written it down, but he thought it was so simple that he just wrote it on his notebook and had forgotten about it. And so once when they looked in afterwards, when they saw his books and saw that he had discovered this in 1914, then now this theorem is called Wiener-Kinchen-Einstein theorem. To kind of and so basically yeah, so this is very useful for us because it tells us, so how do you build a better higher resolution OCT system? You want to make this smaller, narrower. So coherence length you want to make it short. If you want to make the coherence length short, use a broader bandwidth light source which has more wavelengths. So you want to make a laser or a light source. So there are different kinds of light sources. I think I mentioned it in a previous class. So you can use LEDs, you can use laser diodes, you can use lasers. There are different ways. You can use light bulb, like a old incandescent light bulb, like what's called a black body source. There are different halogen lamps. There are so many ways of which you can create light, right? Each one has advantages and disadvantages. But typically we use lasers. Lasers are much more powerful and much more versatile than other sources. But if you want to make it cheap and less expensive, you can even use LEDs or what are called superluminescent diodes, SLDs. So those are kind of commonly used if you want to reduce the cost and still have some other properties and stuff. Okay, so there are different options you can use, but basically whatever it is, you want more resolution, use larger bandwidth. The reason is the Wiener-Kinchen-Einstein theorem. It says that the larger the frequency range or wavelength range you use, the better your this width will be. It's called the kind of the width of the coherence function, and that is essentially what determines the resolution along Z in OCT. The XY resolution is decided by your lenses. What lens you use determines the XY resolution, but what resolution along Z you get is determined by the width of your source. Okay, those are the results from the theory of OCT. This is what, after doing the theory, that's what people figured out. What do you need to do to improve your resolution? The answer is make the source broader. So this is the mathematical relationship between the coherence function and the spectrum. Yeah. So I won't derive this, but there is a way to actually figure this out. This is the equation for the resolution of OCT along Z direction. Okay, so let me ask you to ignore some of these things and just focus on this. Okay, focus just on this portion. Okay, so the crucial thing is there are some constants which come from the theory, but the most important part is this LC, which is essentially your resolution of your along Z for your OCT, is proportional to lambda naught squared divided by delta lambda. So what does this mean? Lambda naught here is central wavelength. So meaning, let's say you have a laser which has a range of wavelengths. If you choose the middle wavelength, that's called the central wavelength. So that is lambda naught, and the resolution depends on lambda naught square, and delta lambda is what's the width of this, what is the range of wavelengths in your source. Okay, so lambda naught divided by lambda naught square divided by delta lambda. So what does this tell you about resolution? If you want better resolution, this number should be smaller, right? Better resolution means smaller number of LC. So if you want to make resolution better, delta lambda, the width of your resistance should be bigger. Or alternatively, you can make lambda naught smaller, or a combination of the two. Right? So if you use a 850 nanometer source, that is the central wavelength, and the bandwidth, say 100 nanometer is the bandwidth. So you can plug that in, and you can do a calculation. What is the resolution you will get? So instead of 850 nanometers, you want to use 1.3 microns or 1300 nanometers. Then lambda square is bigger, so the resolution is worse. And for that, you can choose how much bandwidth there is as well. So why would you want to use longer wavelengths instead of why not just use the smallest possible one? You remember there's a other thing which is your scattering, and therefore the depth to which you can go is another consideration. You want to go deeper, you want to use long wavelengths, but when you go to long wavelengths, resolution becomes worse. So it's kind of, you have to, depending on exactly what you want to see. In cancer, what are the features? What size of features do you want to see? Or how deep are the features inside? Is the cancer growing deep inside, or is it on the surface? So based on the specific problem or the retina, how precisely do you want to measure the thickness of the retina? Or how deep other things you want to see below the retina, right? So there are these kind of considerations, and therefore by choosing different, there are trade-offs you can make. By choosing the central wavelength and the bandwidth, you can kind of choose the resolution you will get from your imaging system, and that's how you decide the resolution of your OCT system. Questions on that? Good. Yeah. So this, as I mentioned, are called the DC terms, which are the constant. So in the data that you collect, if you think of it as collecting data as a function of time, it will be something of this sort. So there will be a DC offset, which is the constant part, and then there is this oscillation, which is because of this what's called the cross correlation. This will be a cosine function, which depends on the difference between the reference arm and the sample arm distance. So basically, like the n equal to 1 will give you this, n equal to 2 will give you this, and so on. N equal to 3 will be another one. So each of these bumps here will correspond to one of the terms in this function. And this is, and then the other terms are small, and so these are the autocorrelation terms, which are typically ignored for it's a reasonable approximation that they're small. And yeah, so that's and if you want to show this graphically, if you use a spectrometer and make a measurement, what do you see? So these are different spectrometer detectors. So different, say, detector 1, detector 2, 3, 4, and so on. If you put a prism and split the light into different wavelengths and look at just the raw data that comes out of the spectrometer, it looks something like this. In fact, you can do this, like sort of plug the spectrometer into like an oscilloscope and actually look at the profile of the data you get. It looks something like this. So basically, this is the light source. Let me use a different color here. So there is an overall DC background, and on top of the DC, there is like a AC oscillation on top. So there's the overall source profile. On top of that, there is a variation. So instead of a constant, and then on top of that, DC, like sort of, it's like this curve, and it's like there is one sinusoid on top of the thing. Similarly, if you add multiple sinusoids, you get this kind of line. Okay, so this is Yeah, so this is, and then you take the Fourier transform to get the, so if you take a Fourier transform of this, you will get this burst. Okay, so like say, do the Fourier transform of this and you get your burst of data. Question? Okay. Yeah. So, so previously I plotted this as a function of frequency. Now you do the Fourier transform and you can go back, or the inverse Fourier transform, and go back to the Z domain. So this source, if the source was uniform, you would have a pure sinusoid if you have one that reflected. But if you have this kind of a source which is like, then it will be like this. So now take this data, do a Fourier transform, and you get like one peak and like another peak and so on. So inverse Fourier transform or Fourier like IFT, so the frequency becomes Z domain again, spatial Z domain. So this is the DC term, this is the cross correlation term, this is the autocorrelation. So you have delta. So you let me like this is a easier way to look at it. So basically these are the autocorrelation terms are very small. Then this is the first reflection, this is the second reflection, and so on. So basically there are cross correlation terms after here, but you might remember from your Fourier Fourier transform, there is what's called conjugate symmetry. So when you take a Fourier transform, there is a mirror reflection. So the left hand side and the right hand side are kind of mirror reflections of each other. So you like basically get kind of, it's just because of the nature of the Fourier transform. So they basically you keep one side and ignore the other side, and those are the only layers there. So that's one of the disadvantages of this time domain, or like compared to time domain OCT. When you do this Fourier domain OCT, where you take a Fourier transform or inverse Fourier transform, and when you do that, like one side is a mirror reflection of the other side. So half the data is basically lost, or at least you have to you need to discard half of it because it's just a repetition. It's a mirror reflection of the other side. So in that sense, you have so the data that you get is basically constants and gamma of like this difference in distance. The gamma of difference in distance like to the second layer, first layer, second layer, third layer, and these are the cross layers. So if you look at that data, so this is gamma of the first one, gamma of the second one, and so on. So first layer will give you one gamma, second one this shape coherence function, second one will give you a second coherence function, and this is the location of the reference mirror, sample layer. So 0 is the reference mirror. This is the sample first layer, this is the sample second layer, and so the height here is proportional to how much of reflection happens, or how much of scattering happens from that particular position. So if it scatters a lot, if that layer scatters a lot, when does it scatter a lot? Whenever there is a big change in refractive index. Scattering happens when there is a sudden change in the refractive index. And so if there is a big change in refractive index, you'll get a big signal. If you have a small change in refractive index, you'll get a smaller signal, and so on. So each layer you'll get these kind of bursts, and therefore you can construct an A scan from this, and then you can construct the 3D afterwards. So this is essentially there's one other thing I'll mention about some practical considerations about SNR and stuff, but this is the essence of how all the different types of OCT, whether you do it in the Fourier domain or in the time domain, essentially this is the basic idea. Questions? No one? Okay. So there are a couple of practical things I wanted to point out. One is that, so if you want to think of the depth over which you get data, because the spectrometer, the detector, has some finite size, meaning It's not like in theory, it's infinitesimally small, right? Like each detector is like very, very thin. But in practice, it's like a big size, like it has a big square size, like each one is a square. So it's not one wavelength that it uses, it adds up a range of wavelengths. Because it adds up a range of wavelengths, this is what's called sensitivity fall off. Meaning, so as you go deeper, the amount of signal that you get from deep range at larger depth, it becomes smaller and smaller, and that's called what's called the roll off or fall off in the image depth. So there is some place where you get the best signal from. As you go deeper and deeper, the signal will become less and less, just because you are using a detector which is not very, like, it's not a perfect detector, a small, infinitesimally small detector. It has a big area and lot of wavelengths fall on it, not just one wavelength. Therefore, so in a graph where you have wavelength or wave numbers, it's like you assume that one dot is exactly one wavelength, right? But it's an average of a bunch of wavelengths in that neighborhood. It's an average of a bunch of wavelengths in the neighborhood. So it's like, because it's not a dot, but it's like an average version of some value. There is some loss of information. So we looked at some of the details in the digital imaging lecture, and so that's the convolution. It basically gets convolved with the size of the detector function. Okay, and therefore there is some, practically there is some loss as you go deeper. That's one problem. Yeah, previous slide. Yeah. Oh, yeah. So sometimes that's interesting. So I'm sorry, because sometimes I say Fourier transform and sometimes I inverse Fourier transform. The thing is, it's minimally important. Meaning, what is the difference between a Fourier transform and an inverse Fourier transform? There's a minus sign, right? That's really the only practical difference, and therefore they're kind of, whether you take the Fourier transform, is like there'll be a minus sign somewhere, and that's it. So in that sense, you take one side data, the side of if you reflect the data, reverse, make it reverse, you will get the same thing. So basically, there is a very simple, the Fourier transform and the inverse Fourier transform are so very similar to each other that which one you take, there'll be just a small minus sign difference. And in that sense, as long as you're consistent, you're okay. Okay, so but yes, I should always say inverse Fourier transform when going from frequency to Z domain. But yeah, I apologize for that, but in practice, it doesn't make much of a difference. Okay, remember, so what's the equation Fourier transform? It's, let me, writing a two-dimensional integral of dx e to the minus pi fx. Yeah? So this will g end of f equals this, right? And then what's the inverse? This is the forward Fourier transform. You can write the inverse, like the inverse as, let's call it h of x as integral df e to the plus the pi here of j 2 pi fx with a different color h of. So what's the difference here? There is a minus sign here and there is a plus sign here. That's the only real difference, right? There is sometimes in 1 over 2 pi, but that's only if you have omega here. So I'm using f here so that there is no 1 over 2 pi problem. And so basically, the forward and the inverse are almost exactly the same. So instead of f, you make it minus f. So here, if you have f, you put minus f here, then you will get back this, right? And therefore, it's reversing the frequency axis. And so forward and inverse Fourier transforms are very, very similar to each other. So that's why if I have interchanged, then in practice it doesn't matter, but I should be careful. That's a good question. Yeah. Any other question? Okay, thank you. So the last thing I'll talk about in terms of practical kind of comparison is SNR, signal to noise ratio. It turns out that this is a famous paper by Michael Soma et al. So what they showed in this paper was that if you compare time domain OCT, step source OCT, and spectral domain OCT, they calculate the SNR theoretically for all three cases. In one case, the signal value divided by the noise variance. Okay, signal intensity square divided by noise variance square. Okay, that's the noise variance. You find that if you look at time domain OCT and spectral domain and step source OCT, there is a factor of m divided by 2. M is the number of detector elements inside your spectrometer thing. Okay, so number of compared to time domain, spectral domain is better in signal to noise ratio by a factor of m by 2. Same thing for step source and spectral domain. So spectral domain and step source have identical signal to noise ratio. You can build either one of those and both will work equally well. But compared to time domain, this is much better. So if you add more detectors into your spectrometer, you'll get much better SNR. And similarly, if you sweep across a lot of wavelengths, you'll get much better SNR. So today, the standard is to use spectral domain or step source, because compared to time domain, the signal to noise ratio that you get is much better. What is signal to noise ratio? The quality it's a measure of the quality of the data that you get. Okay, so after this paper established that these are much better, they did a comparison experimentally. They take the exact same tissue, they did time domain OCT measurements for all the same parameters, same power of light incident, same spectral profile, same a lot as everything that you can keep constant. And then they look at the quality of images you get from like same amount of data collection time. Look at the quality you get here, look at the quality you get here. You can see that like the right side much better, higher quality, right? So this is the spectral domain is on the right side. So it's you get much better data quality compared to time domain measurement. That's after this was discovered, people now use mostly the spectral domain or step source OCT time system. Okay, so that's the practical usefulness of this. So once you do that, you can do 3D reconstructions from this OCT data. You can get a lot of information from you can, once you get 3D, you can cut it in different directions. There are data visualization software tools where you can kind of get this kind of 3D visualization that's translucent. You can rotate it and see, or you can get different planes of cross sections. You can do 3D visualization of different sorts, and it helps us visualize data much better. Okay, and for say for example colon cancer or colon endoscopic OCT with for colon, you get data where you do like this kind of it's a tubular structure, right? So you take a cross section this way and you can see different structures in 3D in a much nicer way using this kind of 3D visualization. And the last thing I'll talk about is like one of my projects which I was involved in. So this original work was done by Gora et al, which is and I followed up on the work which was done by previous people. So the basic idea here is how to identify cancer of the esophagus, the food pipe. Okay, so I mentioned so this is the esophagus from the mouth. So one end is the mouth, the other end is the stomach, and so you get the goal is to get cross-section images at different locations so that you can identify cancer. And what I made, like I built I contributed to the optics and electronics of this kind of a device. So you can see there is an electronic wire and there is an optical green color wire, optical fiber, which goes into what looks like a capsule, like it's a tablet kind of a thing. You know, this big like Croson tablet or some tablet of that sort. This is basically something of that size, of bigger, slightly big size compared to coin. So basically, it's some like then there is an optical fiber attached to this optical fiber. So what you do is basically take this and follow it as it goes along. It does a circular scan. So there is a motor here which rotates, and there is a laser, and so this like laser beam rotates, and so it does a circular scan. And if you have a circle and you move it along Z, what happens? It becomes a helix, right? So it does a helical scan of the entire esophagus as it goes along. So it's scanning along this way, and you get every position, you get a cross section